last class. Thanks God. Speaking on your behalf, not mine. Alright, so I would like to first of all clarify a few misconceptions regarding the displacement current and the Ampere's-Maxwell's law. And then I will present an example. Now, in our previous lecture, we introduced the fourth Maxwell's equation, also called the Ampere's-Maxwell's law, which tells us that the line integral of the magnetic field around a closed path, okay, equals mu naught times a connection current, a current that is due to the mobile charge carriers. Let's call this current IC. Okay, so this is the current piercing a certain area. I'll talk about that area, plus epsilon naught times the time derivative of E dotted with dA. Okay, so if I were to make a loop, a closed loop, and if I were to calculate B dot dL around this loop, then this line integral would equal mu naught times the current that pierces the area which is encircled by the loop. Okay, so this is IC, plus it also has a contribution from any electric flux that is changing and yet passing through this area. So there are two contributions to the magnetic field. One is the connection current, the flow due to the mobile charge carriers. And the other is due to changing electric fluxes. Okay, so there could be a connection current IC. Excuse me. There could be a connection current IC and there could be a changing electric flux. So this is an electric flux, phi E, and this is its time derivative. So this time derivative of the electric flux multiplied by epsilon naught plays the same role as a current, and it's called the displacement current. So you can have two different kinds of currents. One is IC and one is ID, the displacement current. And this ID is really epsilon naught times the time derivative of the electric flux, E dotted with dA. Now, which area do I take? I have to integrate this over an area. So if I draw a loop, I can draw many different kinds of areas. One possible area is simply this flat area that is bounded by the loop. Okay? Another possibility is that I draw a fishing net kind of area. I can draw an area of all kinds, okay, on whose outer perimeter lies this closed path. Okay? So if I take the example of this glass of water, the rim of this glass, okay, इसका जो मुंह है इस glass का, it's a closed path in space, and this glass itself is an area. This closed path is on the outer periphery of this area. I can also make this into a dish. This is a closed path and the area is encircled by the closed path. So this area could be anything. It could be flat, it could be bulging out, it could be bulging in. It's an open area, by the way. So with one closed path, I can draw an infinite variety of areas. No matter what area I choose, this formula should still hold. This formula should not vary, depend upon the kind of area that I choose. Alright? And it will depend upon the kind of mobile phone that you're going to use. So, let me recap. The best way of understanding this displacement current is through the example of a capacitor. as we looked at in the previous lecture. Let's look at the capacitor in a bit more detail. Now these are the plates of a capacitor, and current is flowing into the capacitor, but there is no conduction current through the empty air gap between the plates of the capacitor. We know that. Mobile electrons cannot jump across this gap. There is no sparking that's taking place. Okay? So if I would like to take a point P that's outside this conductor, capacitor, and far away, then I can draw a closed path. So suppose the closed path that I draw is vertical, okay? And since I cannot draw a vertical circle on this blackboard, I would just draw its shadow on the blackboard. So this is in fact a closed path, coming in, going out, coming in, and then going around, circling around, okay? It's a closed path. Now this path bounds an area. इस path के अंदर कोई ना कोई area है. Now, there are different possibilities of choosing the area. One possibility is that the area is the flat area. Okay, so this is a vertical path, and if I draw another figure, this is the path, let's call this path P. Okay, this is the path, and this is the vertical area. Okay, and this area is just inside the parallel plate capacitor. Okay, now I can calculate B dot dl about this path. Now B dot dl about this path, B dotted with dl closed path equals mu naught times. Now what, if you look at this area, the area bound by this path, what's the conduction current piercing this area? Zero. There's no conduction current piercing this area. No current is flowing through this area. But I'm talking about conduction current. There are no mobile electrons or charge carriers that are crossing this flat surface. So I get zero for the conduction current. However, there could be a changing electric field. If the current is time dependent, we know that it will change the surface charges on the capacitor. That will change the electric field. So there is an electric field between these parallel plates. Okay, the direction of this electric field is, if this is a positively charged plate, the electric field is in this direction. Okay, so if the current is changing, the surface charge is changing. The surface charge is changing, the electric field is changing. So now the electric flux that is piercing this area is changing. Okay, so that will give rise to a non-zero contribution. It will give rise to a displacement current. Okay, that displacement current is going to be equal to epsilon naught times the rate of change of electric flux. Okay. Now this term will have the same dimensions as IC. So this is just like a current. A changing electric flux plays the same role as a conduction current. Okay. So in this area, if I take this path and this area that is bound by the path, there is only changing electric field, which means there is a displacement current, but no electric current piercing this path. So I get mu naught ID. Okay. This ID in the previous lecture we found out is going to be equal to IC. Okay. Because if I choose another area, if I chose this to be my area, right? If the path remains the same but the area now changes. Now this is my area, let's call this area S. Okay. Now I have a fishing net kind of situation in which I have a path and in which the area on whose boundary lies the path does not see any electric field. So this is the area. It's a bowl shaped pattern. I have, if I were to draw it in more suggestive terms, this is what it would look like. This is my path P and this is the area. Okay. Now this path is on the outer edges of the area. Alhamdulillah. This path is on the outer edges of this area. I'm equally well qualified to choose this area. I don't have to choose a flat area. But for this particular case, if I were to draw the parallel plate capacitor, the plates of the parallel plate capacitor, if this is my parallel plate, this is the other parallel plate, and these are the connecting wires to the capacitor, and this is just a hypothetical path drawn between the plates. This is my area. Now through this area there is no electric field, let alone changing electric field. There is no electric field because all the electric field is confined, if the distance between the plates is small, just to this area. But none of these electric field lines pierce the area. So as far as this area is concerned, there is no displacement current, there is no ID. Okay. However, there is a conduction current IC that pierces this area. So if I use the Ampere's law, B dot dl for this area is going to be mu naught IC. And IC is equal to IT. This is something we proved in the previous class. So no matter whether I choose this area or I choose an area that solely lies within the plates of the capacitor, I get the same result. So the result is independent of the kind of area that I choose. In each case, the formula, the Maxwell's equation that I've written at the top holds true. Now you might argue, a question was asked by the gentleman sitting in the front, that here you also have an electric field. Right? आपने पूछा था ना सवाल? हाँ, यहाँ पे electric field है. Now you have to see if associate with this electric field, you can associate a flux. Now you have to find out the changing electric flux in this region. Okay, that changing electric flux is actually driving the conduction current. Okay, so you can either use the conduction current or the changing electric flux, but both of them are equal. So if you choose this area, there's no need to look at the changing electric flux, it's just the conduction current. Okay, now if I choose another kind of area, for example, if these are my parallel plate capacitors, the parallel plates, what if my area, this is my closed path, what if my area now looks like this? G, you're going to give me an answer? If you look at this example, if this is IC, the same IC flows through this area, but then you have additional contribution to the changing electric flux inside this area. Because in this area there is an electric flux, in this area there is an electric flux, and it's a changing electric flux that is piercing this area. So would you get the same result? Ideally you should get the same result, but now we have an anomaly, we have a paradox here. There's a conduction current that's going in, the conduction current is the same as the current here, but now there are additional contributions from the changing electric flux in this narrow region and in this narrow region. Because here, this area is inside the gap of the parallel plate capacitor, so there is a changing electric flux through this section of the area, and there is a changing electric flux through this section of the area. So you've already catered for IC, but then you have additional terms due to these changing electric fluxes. So how do you reconcile this fact? The formula should not depend upon what kind of area you choose. Do you understand the question? If you understand the question, you know the answer. Do you understand the question? Question समझ आया? अब बताओ. समझो. देखो, if I choose this area, everything is clear. There is an IC. Okay. If I choose this area, everything is clear. There is no IC. There is only ID. And ID and IC are equal. So I get the same result for the right hand side of the Maxwell's equation. In one case, this term is 0. In the other case, this term is 0. Okay? Now if I'm choosing something intermediate, I'm choosing an area like this. There is the same conduction current that's going in, but there are certain regions in which there is a changing electric flux piercing the area. This blue line, this blue is which represents the area through which we would like to calculate the right hand side. So the same conduction current going in, but there's additional contribution to the changing electric flux. So the right hand side will go up. How will I reconcile this fact? No, they can't cancel out. In both of these cases, if this current is going up, the electric field is pointing in this direction. The fluxes can't cancel out. The area is also pointing in the same direction. The flux is G. Through here? No, it does not decrease. It's the same situation. No, it's the same. No, what is this? It's a wire that is piercing this area. It's the same charge that is brought in per unit time. Any more ideas? Good, at least you've understood the question. Any more ideas as to what the answer could be? How can we resolve this paradox? No, why not? There's an IC and there's a changing electric flux. Here there's a changing electric flux, it's due to an IC, no doubt about it. But you have to take into account all the currents that are piercing this area, displacement as well as conduction. No. G, it is one. G? And ID. Yes, but IC is the same. IC is not diminished. IC कम तो नहीं हो रहा. अगर आईडी की वजह से भी कंट्रीब्यूशन आ रही है कुछ ना कुछ, लेकिन आईसी कम तो नहीं, आईसी तो उतने को उतना ही है, तो टोटल राइट हैंड साइड बढ़ जाएगी. जी, ये वाला ये दो दफा तो ले भी नहीं रहे. देखिए मैं इसको एक साइड व्यू बनाता हूं इस पैरेलल प्लेट का. नाउ आई एम गोइंग टू ड्रॉ the current density, the conventional current density for the conduction current inside this wire and this parallel plate. Here is what the current density looks like. This is the direction of the current flow, right? Now what happens here? The charge has to reside uniformly distributed on this parallel plate. So it goes like this. Okay? If charge is to be stored, then there must be some incoming charge in this region. There must be some incoming charge in this region. Now if I draw a cross section of my loop, this is what is happening. Here some current IC is coming in, right? Here some current is going out of this path. Let's call this current I1. Here some current is going out of this area. Let's call this current I2. Now there is IC coming in and there is I1 going out and there is I2 going in. So the total conduction current IC dash that pierces this path is going to be IC minus I1 minus ID. And this net difference is going to be provided by the changing electric flux inside this region. Okay? Okay? So in this region there will be changing electric flux that will make up for the lost I1 and I2. Okay, so that still the total current, irrespective of whether it's conduction or displacement, is still IC, which is fed into the right hand side of the Maxwell's equation. Okay, so this is something you really need to understand clearly. Now I would like to give you a practical example of, I would just like to apply these concepts to a toroid. Suppose I have a toroid, a thin toroid, and it has a certain number of windings. The radius of this toroid, say, is capital R, and it's such that this cube diameter is really small. So this is our toroid. Okay. Now we know that if a current I flows through this toroid, a magnetic field is established. So if this is the direction of the current, okay, then the magnetic field is going to point in this direction. So it's going to be circulatory magnetic field, okay, like this. Tangential, sorry, in the opposite direction. It's going to be circulatory magnetic field, a tangential magnetic field, a cylindrically symmetric field in this direction. Let's call this field B1, okay? This field pattern is B1. We know what this field is. This field B1 is mu naught n turns I is the current divided by 2 pi r. Ampere's law, simple Ampere's law, because there is no changing electric field here. Simple application of Ampere's law. Now if I look at this path, if I draw a hypothetical path or an Amperian loop, now this is my path B, and there is some current that is piercing the area. The current that I am taking is now the current that flows in these solenoidal wires. So there is a current that is going in here, and a current that is going in here, and a current that is going in here, and all of these are conduction currents, ICs. There is no displacement current. So this is an Amperian diagram of the same situation. I draw a path, and there are n segments of wire that are carrying current inside, and it pierces the area that is bounded by this path. Okay? So I use the Ampere's law and get this formula. This is B1. Now suppose I do something different. समझ आ रही है? ये Amperian diagram की समझ आ रही है? So now I do something different. I put all of this inside an electric field. Suppose the electric field is pointing suppose the electric field is pointing in some direction. Suppose the electric field is pointing out of the plane of the paper. Okay, so this is E, pointing out, and it's uniform everywhere. So I bathe this toroid, which is carrying a current, inside a uniform electric field. If this field is changing, then the condition will actually change. If this field is static, the electric field is static, the magnetic field B1 is going to remain the same, because there is no changing electric field. However, if I increase the electric field, for example, at some rate, for example, the rate of increase of electric field is dE by dt, and it is becoming bigger and bigger in magnitude and still pointing in the outward direction. Now I have a different kind of current, which is the displacement current, because I have a changing electric field. Okay, a changing electric flux, in other words. Now I have to apply the complete formulation of the Ampere's Maxwell's law. I would have to take into account the second term on the right hand side. Okay. Now if I were to calculate the displacement current ID, it's going to be epsilon naught times d by dt of the changing electric field. E. Now area, it's a uniform field, so I can just take the area of this circle. It's pi r squared, and there's a d here. So the electric field and the area vector, they are parallel to one another, and I have to figure out the direction later on. Okay, so the electric field and the area vector are parallel, so the dot product just involves multiplying E with pi r squared, and this E is uniform over this space. It's uniform over space, although it's changing with time. Okay, so this is the time derivative. I get epsilon naught pi r squared dE by dt. Now this is a different kind of current. Okay, this is also a current, even though there is no there could be no battery connected to this solenoid. If I open the switch and this toroid was connected to a battery and now it's no longer connected to a battery, the current, the conduction current to the toroid will cease. It will not exist. However, if I apply an electric field, I don't need to apply a battery. I don't need to apply a conduction current that's flowing through the circuit. The changing electric field will play the same role as played by a conventional conduction current. Okay, and I can calculate what this displacement current is. It's proportional to the changing electric field. So I can draw another Amperian path. If I draw another Amperian path, this changing electric field, I can find out it's just another current. So this current is also piercing this loop. Now I have to see whether it's coming out or it's going in, whether it will add to the magnetic field or will it subtract or lower the initial magnetic field B1. Alright, let's see that, whether the displacement current is coming out or it's going in. Now the electric field is coming out. Okay, this means that dE by dt is also coming out. The electric field is increasing, coming out. So the current has to we have to decide whether the current, displacement current is coming in or is it going out. What are your guesses? How can you find out what direction is the displacement current flowing in? In or out? Okay, I give you 2 minutes to think about it. No, Lenz's law will not be applicable here. So the rule that you would use here is actually a rule of thumb. Now, if your thumb points in the direction of dE by dt, now dE by dt is coming out. Okay, dE by dt is coming out. Okay, because this electric field is coming out and it's increasing coming out, so my thumb has to point out. Now these fingers wrap in the direction of the magnetic field. Okay, now if this is the direction of the magnetic field that is produced by the displacement current, let's call it BD, then if I were to associate with this magnetic field a displacement current that is coming out of this or going into this area, what direction would it point in? It should point outwards. So my current is going to point outwards. This is my ID. is pointing outwards. Now, this electric field, remember, was dispersed in space. It was everywhere in space. It was homogeneously distributed in space. So I've replaced all of this electric flux by just a hypothetical conductor that is carrying a current ID. I'm equally justified in doing so. I can replace all the electric flux, the changing electric flux, by a hypothetical conductor that is carrying the same amount of conduction current, right? It's ID. So I replace the changing electric flux by just a wire that is coming out, bringing current out, and it's piercing this area and it's carrying a current ID which equals this. Now I have two scenarios. I have a conventional current or a conduction current which is N times I going in. Okay? So I have a conventional current N times I. This is the current IC going in. Okay? This current is going in. And I have a current ID coming out. So NIC plus ID into mu naught will give me B dotted with 2 pi R. This will be my Maxwell's equation. Sorry, NIC, I'm sorry. B into 2 pi R. So I have to look at the signs here. B 2 pi R is positive, which means I'm looking at currents in this direction. Okay, I'm looking at the magnetic field in this direction, which will be produced by an ID coming out. So this is positive and this is negative. So B into 2 pi R is what I've written over there, and the total electric field is going to be 1 over 2 pi R minus N times the conduction current plus the displacement current, which is epsilon naught pi R squared dE by dt. Okay, so this is the net magnetic field along the Amperian path. Alright, so a changing electric flux plays the same role as a conduction current. It stands on equal footing as a conventional conduction current that is carried by mobile charge carriers. Now the best illustration of these effects are through a capacitor. Okay, we've already seen capacitors. And now I would like to show you a demonstration. We know that if we have a capacitive circuit or an RC circuit, alright, please pay attention. This is an EMF, a source of EMF, no changing magnetic field, because changing magnetic fields also produce an EMF, okay, which is the Faraday's law. So this is a normal battery of EMF E, this is a resistor R, this is a capacitor C. If I close the switch, I already know how charge builds up on the capacitor. If I close the switch, initially what's the charge on the capacitor? Suppose it's 0, that's my initial condition. With time the charge slowly builds up. Okay? Now what happens to the current with time? If I were to plot, okay, let's make nice plots. Time, current. Time, current, I. Okay? So with time, I close the switch, the charge builds up. What happens to the current? It starts from its maximum value and decreases with time. Okay? Why does the current have such a kind of behavior? आप बताओ, करंट का इस तरह का बिहेवियर क्यों होता है? I don't know what's an open circuit. I don't want to hear your explanations from circuit theory. What's an open circuit? I want to understand in the language of electric fields. Hard. Exactly. Initially, the capacitor is uncharged, it has no fringe electric field. So it's as if the capacitor is not there. All the electric field is inside the wires. So I close the switch, all the electric field is inside the wires. There is no fringe field here because it hasn't built up any charge. As soon as it builds up charge, it produces a fringe electric field that opposes the electric field that is produced by the surface charges on this wire. So the net electric field inside these wires decreases. When the net electric field decreases, the current drops. Okay? So that's why the current drops exponentially. Now what I do is I open the switch, but then I immediately connect another branch into the circuit. So I open this switch, and when I open the switch, at the same time I close the switch. Okay. Now what's going to happen? Charge has already been built up on this capacitor. It's going to discharge. Okay. Now could you tell me what's going to happen to the charge that builds upon this capacitor? It will decrease. The charge built upon the capacitor is going to decrease. It's going to drain away. Because now the only electric field that exists in this wire is from the fringe field. And the fringe field will drive current. Okay? So, when I open the switch and close the switch, the charge is going to drop. Now, if this is the current through the resistor I, okay, this is I, the current through the resistor, okay, I can call it IR. Could you please plot on your notebooks what's going to happen to IR when I reverse the switches? What's going to happen to IR? I close the right switch, open the left switch. If you don't mind, I'd like to take 15 minutes extra today. Okay? Good. Is this from memory or from thought? From thought? Haven't you studied RC circuits in the circuits? No. Good. सफेद तब पलटें जब सर पास से गुजर गए. Now what's going to happen is that this capacitor has built up some charge, so positive charge. Now this capacitor, if it has built up some positive charge, there is a fringe field due to this capacitor in this direction. So what this fringe field is going to do, it will drive current in the opposite direction from the original direction of current. So current will switch its direction immediately. From positive currents, it will start from a negative current. And now the electric field, the fringe field from the capacitor is maximum. So it will produce a maximum electric field in the neighboring wires. The current will be maximum, but in the negative direction. And then when it loses off its charge, the fringe field decreases. When the fringe field decreases, the electric field it produces in its neighboring wires, which then propagate throughout the circuit, is going to decrease, and the current is going to decrease. So this is what's going to happen. Okay, this is an exponential decay, some I naught E minus T over RC. This is also an exponential decay. Okay, minus I naught E minus T over RC. Okay, this is also proportional to the voltage across the resistor because of Ohm's law, and this is also proportional to the voltage across the capacitor, which is just proportional to the Q. So this is the kind of pattern that you expect to observe when the switch is opened and closed. But now I have a circuit for you in which instead of switches opening and closing, I have a square pulse that is applied. So the pulse is on, off, on, off, on, off, on, off. Okay? When the pulse is on, it's just like that the switch is closed and this is off. When the pulse is off, then the capacitor discharges through the computer, in fact, because I'm applying a pulse through the computer. So I would expect to see this kind of behavior. Let's see if I get this. This is my circuit. Okay, over here. It's just a simple RC circuit. Okay, there's a resistor and a capacitor, nothing more to it. Okay, let me turn off the lights for a while. Alright, so what we see here is that I've applied a square pulse of amplitude 3 volts, so it remains on for 3 volts for a certain period of time. The frequency of this pulse is 3 Hertz, the amplitude is 3 volts, then it switches off. Now this is the voltage across the capacitor, which is proportional to the charge on the capacitor. When this pulse is on, the capacitor is charging, the voltage across the capacitor is rising in an exponential function. The time constant for this rise is equal to the resistance times the capacitance. It rises. Then I switch off the pulse, the capacitor starts to discharge. When the capacitor starts to discharge, the voltage across the capacitor, which is proportional to the charge, drops. Okay? And it starts to go towards zero. This is in fact the current through the circuit, through the resistor. I've plotted the voltage across the resistor, which is proportional to the current through the resistor. Now, initially the current is maximum, and as the capacitor is charged, it builds up its fringe field, the current through the wires decreases, and then as I switch off this pulse, the current reverses its direction and starts flowing in the opposite direction. So this is exactly a nice demonstration of an RC circuit. Now I'm going to change the resistance a little bit. So what I've done here is that I've increased the resistance. So the response is slower. So the amplitude to which it rises is smaller. In the same amount of time, it just rises to 0.8 volt even though I've applied 3 volts. Because its approach towards its maximum voltage is decreased. So I'm increasing the resistance even further. So this response becomes slower and slower, more and more sluggish. It does not reach to high enough amplitudes before it switches its direction. Now if I decrease the resistance, let's see what happens. The response becomes faster and faster. I'm reaching 1.2 volts. The maximum is 3 volts. Look at the second graph. Okay? The response becomes much and much faster. Now I've reached 2.5 volts almost in the same amount of time, which means that this slope of this line becomes sharper and sharper, which in other words, the time constant decreases. I'm making my response faster and faster. And look at the current. The current is rapidly decaying because the charge that is quickly building up on the capacitor. Alright? So, in this second demonstration, which most of you have already seen in your physics laboratory, is just the demo for Faraday's law. In this demonstration, what we have is that we have a Hall sensor, we have solenoids, two different kinds of solenoids. One has 30 turns, the other has twice the amount of turns. So this Hall sensor is measuring the magnetic field, and this is measuring the rate of change of flux. So it's a demonstration of Faraday's law. And we have magnets at the bottom. If I turn this wheel around, then you can see what the different patterns obtained, the voltages that are obtained on these different kinds of sensors are. Okay, so I'm going to run this. Okay, so on the top and the middle graphs, you can actually see the EMFs that are developed from the changing fluxes through the solenoids. And on the bottom graph, you can measure directly the magnetic field through a Hall sensor. And this is a quick question for a quiz. Why does the graph on the top or on the middle looks like it goes negative and then it goes positive? Okay, so these are permanent magnets that are flowing, or they are moving, circumambulating around solenoids, which change the flux through the solenoid and which give rise to positive and negative currents. I make the wheel spin faster and faster. These pulses will go higher because the rate of change of flux goes higher, and also the fluxes go. Also the areas, however, remain the same under these positive and negative dispersion curves. Okay. On the bottom you see the magnetic field directly, and the top and the middle curves are the rate of change, are the derivatives of this function. Okay, so let's move on. Now I would like to, I have 2 or 3 things in mind, but I would probably go to the very end, and I will leave the discussion of the inductors for Noor in tomorrow's recitation. But I would like to just point out one fact, is that energy is stored inside electric fields. We know that. So if you have an electric field, the energy inside this electric field per unit volume, small u, is half epsilon naught E squared. Ali, इसको बैटरी जरा बदल देंगे ना, तंग कर देंगे. So this is the electric energy stored inside an electric field, for example, between the plates of a parallel plate capacitor. Now, if I have an inductor with a certain inductance L, there is energy stored inside the magnetic field of this inductor. Okay. Now the energy stored inside the magnetic field, UB, okay, per unit volume, this is specific energy, is given by half, analogous to epsilon naught, I have 1 over mu naught, okay, and analogous to electric field, I have B squared. Okay, so this is the energy stored inside a magnetic field. All the energies are stored inside fields, electric fields, magnetic fields. Okay. Remember, now this is a formula that whose derivation you'll see tomorrow in the recitation. Okay, we'll derive this formula. So suppose I have a capacitor and I have an inductor, C and L. Now we know that this formula is actually equal to half CV squared for a capacitor. Okay, this formula equals half Li square for an inductor. Okay. Now if I have a circuit which connects a capacitor and an inductor, and the capacitor is initially charged, it has some energy, it has some electric energy. Now where is that electric energy? It's inside the field. There's an electric field inside the circuit which possesses energy. So stop thinking that the energy is possessed by electrons. The energy is, the electron has a potential energy and a kinetic energy, and this is the energy of the system. The energy resides in the fields, we know that, okay? So fields are a real concept, they carry energy. So all of this energy is inside the capacitor, and there's no magnetic field here. Okay? Now what's going to happen is that this energy will be transported to the inductor. Because if this is initially positively charged, and this plate is negatively charged, it carries some energy which is half CV squared. Now what we have a circuit comprising an effective battery and an inductor. This will make a current flow through the circuit, right? Because this will produce a fringe electric field. This fringe electric field will make a current go around the circuit. Now when the current goes around the circuit, its energy goes up. The magnetic field then starts gaining energy. But when the magnetic field starts gaining energy, because the current has gone up, its charge is depleted. When its charge is depleted, the voltage across it drops, or the electric field here drops, and it loses energy. So the capacitor is donating its energy to the inductor. Okay? And then the inductor will donate energy back to the capacitor. So this is like an oscillator circuit. Energy is oscillating between the capacitor and the inductor. It's just like a pendulum. The energy is being exchanged between the potential form and the kinetic form. Here energy is changing its coinage. It's just changing its demeanor. It's changing its appearance. It's residing in the electric field, then it resides in the magnetic field, then it goes back to the electric field. So there's a constant toggling between the energies. And if I were to plot a graph between versus time between the electric energy stored in the capacitor, this is going to be a cosine squared curve, and the energy stored inside the inductor is also going to be a sine squared curve. So there is constant toggling of energy between the electric and the magnetic fields. This is the formula that we're going to derive tomorrow. Okay? Now this toggling ensures that the total energy remains constant. This is E total. Okay? Now with this background, I would like to discuss energy flow in simple circuits. In simple DC circuits. And this will be the final point of discussion in our course. Okay? And this concept is not covered in your textbook. And it's not covered in most textbooks that you find. By the way, I've never seen a textbook that covers this idea. So you have to pay close attention. And I would like to connect energy with fields, because fields has been our central concept. I connected currents with fields, fields inside conductors, and I connected it with the surface charges on conductors. Now I would like to see how does energy flow in a real circuit. And I would like to invoke your current understanding. And I would like to invoke, bust any myths that you already possess about how does energy flow inside electric circuits. And I'm not going to talk about complicated RC, RL circuits or RLC circuits or oscillators. I'm going to talk about simple circuit, a battery connected with a resistor. That's it. So let's draw such a circuit. I have a battery. Suppose this is the positive terminal, negative terminal. Now I have connecting wires, thick wires, and I have a resistor. A resistor can be modeled by a thin wire, correct? Like a light bulb. So this is my insidious simple circuit, nothing more complicated than that. जो बट रही होगी आपकी ठहरे. All right. Now, if this is a light bulb, it glows. This means energy is being transported here. I can warm my hands with this light bulb. Where is that energy coming from? Ideas. डरना नहीं है. हाथ खड़ा करें और बताएं. कौन लेके आ रहा है? कौन कासिद कौन है? पैगाम्बर कौन है? कौन सा पैगाम्बर है जो पैगाम लेके आता है? यार ये ले लो. ठीक है, आप किताबों में देखते होंगे बाल्टियां उठाई में छोटी छोटी परियों ने वो एनर्जी लेके जा रही हैं, बल्ब को दे रही हैं और फिर खाली बाल्टी वापस आ रही है. आइडियाज कहां से आ रही वो एनर्जी? बताएं पीछे से कोई. Where is this energy coming from? Right? The energy has to come from somewhere. Energy has to be conserved. There must be some source of energy. Right? Okay. Batao. From the electric field created by the batteries. Now, there's an electric field here. If this is a superconductor, alright, forget about super. There's an electric field here. Is energy being wasted here? But who brings this energy? What's the source of energy? What's the source of the energy inside the electric field? What's the origin? The electric field inside the battery. But with time, the electric field inside the battery does not diminish. If the electric field inside the battery diminishes, then you will say that the energy is coming from the electric field inside the battery. Chemical reaction in the battery, okay. So suppose there is no battery, there is a changing magnetic flux piercing this circuit. Where is that energy coming from? But if it's coming from a magnet and it's changing, I'm rotating a magnet like this, so it's changing the magnetic flux to this circuit. If it's giving off energy to the light bulb, the magnet should cool with time because it's giving off its energy, but the magnet does not cool with time. Alright, so what we understand here is that there is some input of energy. It's either the chemical reaction of the battery, or if it's a changing magnetic flux, it's some mechanical agent that is driving the source that is changing the magnetic flux. So there is some agency that is inputting energy. Now what I would like to argue is that the conventional in textbooks, what you would see is the following. If this point is A, this point is B, C, D and back to A. If I plot the potential energy, okay, V, the potential V along the path of this conductor for a positive charge, at some point A, it's at some potential, its potential rises to B, right? This is point B. It goes up to B, okay, it rises, the potential rises because a positive charge, which is the direction of the conventional current, has to increase its potential in going from A to B. Then it coming from down from B to C, its potential drops, okay. So C is far away as compared to B, so A and B are close, C is far away, and the potential then drops. But the drop is really small because the resistance of this wire is small. So it drops, but doesn't drop appreciably. This is how the potential drops. Now from C to D, the electric field here is large, the resistance is large, so the potential drop is large. Okay? So from C to D, it drops in its potential even further and sharply. And from D to A, it drops back again and comes back to this value. Okay, so this is at the same datum line, okay? So this is our conventional wisdom of how the potential of a charge that is transported around the circuit changes. And associated with this potential is the potential energy, Ux of an electron, of a proton or a positive charge that's circulated around the circuit. So here the potential energy goes up, here it loses its potential energy across this resistor, and that makes the light bulb to glow. And then its potential energy drops a little bit, but this is a really simplistic argument, and it's totally wrong. This is not how energy is transported in electric circuits. First of all, it does not describe the speed of energy propagation. You turn on the switch, this light bulb glows immediately. And if this were to be transported by the drifting electrons or the drifting charges, the flow of energy, the rapid flow of energy transfer cannot be explained by this model. The second point is that what's so special about energy flowing from BC to D? Why can't energy flow from A, D to C? And in nature, there's no difference between positive and negative directions. Why this asymmetry between positive and negative charges? Okay, so why does energy have to flow from B to C, and it loses all of its energy here, and then it crawls with a minimalist energy back to point A? This is an incorrect reasoning. What's so special about this direction in the circuit? Why can't energy flow in this direction? Okay, this is another anomaly with this approach. This approach fits in well with our modeling of electric currents through waters through drain pipes. In old textbooks, you would actually find that you model a current by water flowing through a pipe. So the water is at a higher gravitational potential energy here. It falls down, gives away all of its potential energy in the form of kinetic energy, and then just starts crawling down with minimalist potential energy back to the source. So this reasoning does not really work. So there has to be an alternative reasoning. The other problem is that if I replace this battery with an AC source, right, still this bulb will glow, right? So in an AC source, there is really no motion of the electron C. The electron C sloshes to the right, then it sloshes to the left, right, left, right, left. There is actually no drift velocity. So how can energy flow to this light bulb? Because these fluorescent tubes that we have, they're all being powered up by AC sources. So this model, this simplistic naive model, cannot explain how energy is transferred. So we'll have to use our reasoning of electric fields and magnetic fields. So this is the culmination of the entire course. Okay? Now, before I introduce how energy is transferred in a circuit, I would like to introduce to you a concept of the pointing vector. Now, the pointing vector is generally introduced in advanced courses which deal with electromagnetic waves. So the first encounter with the pointing vector comes when you study electromagnetic waves. But the pointing vector is a more general concept. What the pointing vector tells us, it's a vector denoted by S. It tells us the direction of energy flow. So if this vector S is pointing in this direction, this is the direction which energy is flowing. If this vector points in this general direction, this is the direction in which the energy is flowing. And this vector S, which is in honor of pointing scientist, is equal to 1 over mu naught times the cross product of the electric and the magnetic fields. Okay, now this derivation is beyond the scope of this course, but you study this in your next course on electromagnetism. But this is what the pointing vector tells us. Okay, 1 minute. So it's a cross product, so it's a vector. It has to be a vector because it tells the direction of the energy flow. Its units are watts per meter square. So if I have an area, some area A, okay, and the pointing vector is pointing in this direction and it's normal to the area, then the total power that goes across this boundary is going to be S times A. S is per unit area, I multiplied with the area. This is the total power in watts that goes across this surface. Okay, so this pointing vector tells us the direction of energy flow, it tells us the amount of energy flow, and it's the cross product of E and B. Okay, now let's use these rudimentary concepts and build up our idea of how energy actually flows inside this circuit. Gee, there was a question. Okay, most of this argument you already know, so you'll easily follow what's going on. Positive terminal, negative terminal. First of all, with this yellow chalk, I'm going to draw the electric field inside this circuit, inside the circuit. Electric field in steady state, DC source. Correct? Constant electric field, large electric field, but constant inside this resistor, large. Okay? This electric field is the same as this. All of the electric field inside this conductor is the same. Inside the battery is pointing in the opposite direction. This is the electric field inside. Okay? Which maintains the current flow. Okay? E, this is the electric field, E. Why is this electric field larger? Because the current has to be constant across this interface. Thinner conductors have bigger electric fields. Alright, so this is the electric field. Where is this electric field coming from? आप बताओ. रिजवान के साथ जो बैठे हैं आप बताओ. इलेक्ट्रिक फील्ड कहाँ से आ रही है? चुप करो. ना करो यार. सरफेस चार्जेस की वजह से आ रही है. ठीक है? So there is a distribution of surface charges. Okay? So the surface charges are positive, higher concentration here. There is a gradient. This gradient actually establishes the electric field. Okay? So this is how charge is distributed. Okay? And these surface charges produce the electric field. The charge gradients produce the electric field. The charges here are really small, by the way, but the gradient is large. That's why the electric field is large. Okay? Now what we would like to see is, now if in green I just show the direction of the conventional current I. Okay? It's green, even though current is not a vector, but I really need to draw current density. But in green I'm showing the conventional current, right? This is I, and the I is in this direction inside the battery. Okay? Because the current has to be continuous. So this is the direction of the current. Now I would like to find out the direction of the magnetic field. Now I'm going outside the conductors. Okay? I would like to go outside, step out of the conductors. There is a magnetic field inside the conductors, no doubt about it. But I would like to take a view of what happens outside the conductors. In the immediate vicinity of the conductors, there is a magnetic field. So this current that is circulating will produce a magnetic field. Now what will be the direction of the magnetic field? I'm going on the outer periphery of this circuit. What's the direction of the magnetic field here? Just outside the battery. Into the plane, right? So this is magnetic field, magnetic field, magnetic field, magnetic field, magnetic field. Is this magnetic field the same magnitude as this magnetic field? क्यों? yes, because the same current. ठीक है, यहां पे इस तरह अंदर. So I'm drawing the magnetic field in the immediate vicinity of the outer periphery of these wires. Okay. Now what I would like to do, I would like to draw the electric fields outside the wires, in the immediate vicinity of the wires, but outside. Now where are those electric fields outside coming from? पहला सवाल, will there be an electric field outside the wire? आप बताओ, कोई इलेक्ट्रिक फील्ड होगी? यहां पे कोई इलेक्ट्रिक फील्ड नहीं होगी. क्यों नहीं? क्या इलेक्ट्रिक क्यों नहीं होगी? ये सरफेस चार्जेस नहीं है. अगर चार्ज कंडक्टर है उसके गिर्द इलेक्ट्रिक फील्ड होती है, 1/8 से वो चेंज होती है. माना कि ये चार्जेस बहुत थोड़े हैं, माना कि तेरी दीद के काबिल नहीं हूं मैं, चार्जेस थोड़े हैं लेकिन है तो सही, तो इलेक्ट्रिक फील्ड एग्जिस्ट करेगी बाहर, चाहे वो जितनी मर्जी छोटी हो, क्योंकि सरफेस चार्जेस हैं. जहां चार्ज कम है वहां इलेक्ट्रिक फील्ड भी कम हो जाएगी. नाउ आई वुड लाइक टू ड्रॉ द इलेक्ट्रिक फील्ड आउटसाइड. नाउ द इलेक्ट्रिक फील्ड इनसाइड इज axial. Okay, the electric field inside this resistor is also axial, but it's big. If this is a good conductor, okay, if this is a good conductor, what about this? Is this electric field big or large on relative scale? अगर ये good conductors हैं ये सारे, तो इलेक्ट्रिक फील्ड छोटी होगी या बड़ी होगी? ये सवाल है ना. इलेक्ट्रिक फील्ड छोटी होगी बड़ी होगी? अगर अच्छा कंडक्टर है उसमें से करंट गुजर है, इलेक्ट्रिक फील्ड छोटी होगी या बड़ी होगी रिलेटिव स्केल पे? In order to have the same current flow through a better conductor, do I need big electric fields or small electric fields? I need small electric fields because the current density J equals sigma E. If the conductivity is better, I will need small electric fields to produce the same current density. In superconductors, I don't need any electric field at all. Still current will flow. अच्छा कंडक्टर में इलेक्ट्रिक फील्ड छोटी होगी, बुरे कंडक्टर में और कम एरिया वाले कंडक्टर में इलेक्ट्रिक फील्ड बड़ी होगी. Okay, so these electric fields are really small here. Okay, so I would just, for in an exaggerated view, I will make these vectors smaller. Okay, these are good conductors. Okay, so it's an axial electric field but small. Now I would like to find out the electric field in the immediate vicinity outside the conductor. Okay, I would like to use Faraday's law for that purpose. So let me draw this cross section here. There's an electric field here. Okay, this electric field is constant inside the conductor because the current is uniform throughout the area. Now I would like to find out the electric field outside. Okay, I draw a loop and I would like to apply Faraday's law. What's the electric field in the immediate vicinity outside? Faraday's law इस्तेमाल करना है. ये तो आपकी फिंगर टिप्स में होना चाहिए. इलेक्ट्रिक फील्ड जीरो की. देखो कोई ना कोई चार्ज है यहां पे, जो भी चार्ज है उसको अभी हम भूल जाएंगे. अगर चार्ज ना भी होता, if there were no charge, still there would exist some electric field. Now if you look at this path, I traverse this path in this direction. The electric field here is some E1. Suppose the electric field here is E2. Okay. Now if I'm only taking into account electric fields that are parallel to this conductor. Now E dot dl across this path, it's a closed path. What should this be equal to? Rate of change of magnetic flux through this loop. Is there any changing flux through this loop? Is there any changing flux? No. There is flux but not changing flux because the current is constant. So this has to be 0. Now if this is 0, this means that this E2 must be the same as E1. Okay? So outside the conductor, just outside the conductor, the electric field is going to be parallel to this direction. Here the electric field is going to be large because of this, because the electric field inside is large. Here it's going to be small outside, here it's going to be small, here it's going to be small, here it's going to be small, here it's going to be large. Okay? So I use Faraday's law to determine that the electric field outside is going to be parallel to the electric field inside because of Faraday's law. Okay? But I have missed out an important fact, is that there are surface charges here. These surface charges will produce normal electric fields, because if I have a metal and I have some surface charge here, then it will produce an electric field that is normal to this surface. So outside the conductor there is going to be an axial field, a parallel field because of Faraday's law, and there is going to be a normal field because of Gauss's law of electricity. Okay, this normal field you get from Gauss's law, because then you can make a Gaussian cylinder like this. Okay, and you can find out the electric field. The electric field near the surface of a conductor, you know, is sigma over epsilon naught, where sigma is the surface charge density. So wherever there are charges, there have to be normal fields pointing out. So in the immediate vicinity, there is going to be a large normal field in this direction because the surface charge here is large. Right? There is going to be some electric field here. Yellow shows electric fields. Here, the normal component of the electric field is going to be small because the charge here is small. Here, it's hardly going to be a normal component, a very small normal component, because the charge here is really small. Here the electric field is going to point in this direction, the normal electric field. Here it's going to point in this direction. Okay? So now I have two components of the electric field outside. I can draw the resultants. Let me draw the resultants in a fresh diagram. देखो लॉजिकल आर्ग्यूमेंट है, इसमें कोई बस लंबे आर्ग्यूमेंट्स हैं और कुछ नहीं. लॉजिकल आर्ग्यूमेंट्स है, कोई इतनी खास मैथ भी नहीं है, बस एक कॉन्सेप्ट है जो आपको पास होना चाहिए. Now I'm just drawing the electric fields outside. I'm not worrying about the electric fields inside. यहाँ पे चार्ज है ही नहीं. Okay, so these are the rough electric fields outside. Here the normal component is large because the electric field, the charge here is large. The normal component decreases. The normal component decreases. Okay? Now, the field inside this conductor is really small because it's a good conductor. So everything is being determined by the normal components. Here, there is no normal component because the charge here is really small. It's almost zero. This is the symmetric point in the circuit. There is charge gradient, no doubt, but there is no charge. Very little charge. So all of the electric field here is axial. and then the normal component of the electric field starts pointing in the opposite direction. Here the electric field is all axial. Okay? Now we have already found out the direction of the magnetic fields. The magnetic field here is pointing in this direction, this direction, this direction, this direction, this direction. Okay. Likewise, I can draw the electric field inside the inner periphery. Okay, for example, here the electric field will be like this, but what about the magnetic field? It's going to point out, right? Because of the direction of the conventional current, it's going to point out. Here it's going to point out, 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 out. And the electric field still is going to point like this, this, this. Okay. So this is the pattern of electric fields and magnetic fields in the immediate vicinity of this conductor. The magnetic field drops off as 1 over r because of Ampere's law. You move away from the conductor, the magnetic field drops. The electric field drops as 1 over r because you have charge distribution, so it goes off as 1 over r. The axial component, however, survives. If this is the electric field here, there will be an electric field far away because Maxwell's law has to be satisfied, provided there is no changing flux through this loop. So this is the distribution of the electric and the magnetic fields. Now I would like to plot, or I would like to draw the pointing vectors. Okay? Pointing vector is just a cross product between E and B. So I have my right hand's fingers in the direction of E, which is the first vector in the cross product. I curl them in the direction of the magnetic field. Here, E, B, the pointing vector is pointing in this direction. Now these shaded green arrows are the pointing vectors. Here, the pointing vector is like this. Let's see what the pointing vector here is. It's E cross 2. It's E cross 2. Here, E crossed with B. Here, it's E crossed with E, downward direction. Here, it's going to be in this direction. Here, E crossed with B in this direction. Let's see what happens here. E crossed with B towards the resistor. Here, E crossed with B once again towards the resistor. Beautiful. And I am surprised. E crossed with B. Again, in this direction, the pointing vector is pointing downwards. क्या अजीब सी बात है. Sorry. I give you 1 minute to just look at this diagram and look at its marvel. So we have resolved a lot many conflicts here. We have energy that is emanating out of the battery. Battery में से शुआओं की तरह बाहर निकल रही है. And we have energy that is constantly going into the resistor. Here the energy is just flowing into the resistor. The pointing vector is in the direction of the resistor from all sides. जैसे सब गलियां उसके घर को जाती हैं, सब एनर्जी की सब गलियां इसके घर को जाती हैं. They all point in this direction. Here the pointing vector is pointing in this direction towards the resistor. Here it's pointing in this direction towards the resistor. Because there is no energy that's being lost in these wires, because these are good conductors. All of the energy is, this is the source of energy, this is the sink of energy. Now the concept of pointing vector actually makes this possible. Now if I would like to find out the total energy that goes in here, I can also see if it matches with our circuital description. S is power per unit area. Suppose this resistor has a radius R and length L. Okay? Now the power that goes into this resistor from its magnitude is 1 over mu naught EB. Here you notice that the electric field and the magnetic field are in the normal direction, perpendicular to one another, because there are no surface charges here. So there is no normal component. It's only an axial electric field and a magnetic field that is into or out of the plane of the paper. So this is S. Now what is the electric field? The electric field is simply potential difference IR divided by the length. R is the resistance of this object. What is B? B times 2 pi small r is mu naught I. Okay? So S becomes, this means that B is mu naught over I into 2 pi. S becomes 1 over mu naught. E is I, R, L. And what is B? It's mu naught I over 2 pi R. Okay? Let's do some cancellations. Nice cancellations. Mu naught goes away. Oh, I भी है. Oh, sorry, I इधर है. Okay? Now, this is I square R. Now, what is 2 pi RL? What's 2 pi RL? So, volume is the surface area of this resistor. Right? The surface area of the resistor is a cylindrical resistor. I take, so the surface area into 2 pi RL, I take this here. So this is the power per unit area multiplied by the area. This is the power that goes into the resistor, and it's equal to I square R. It matches Ohm's law perfectly. So you have to believe in this approach of looking at the pointing vectors to discuss how energy is transferred inside electric circuits. Alright, so this brings us to the conclusion of this course. We're going to have a recitation tomorrow, and in that recitation we're going to calculate the inductance of a toroid. Noor is also going to go through quiz number 4. And just one point that I would like to make that has nothing to do with physics. During this course, you just scratched the surface of a landscape. Electric and magnetic interactions are one of the most important interactions in nature. And you remember when Newton gave all his laws, you know what he said? He said, I do not know what I may appear to the world, but to myself I seem to have been only a schoolboy playing on the seashore and diverting myself in now and then, finding a smoother shell or a prettier pebble than ordinary, whilst the great ocean of truth lay all in undiscovered before me. And this was translated by Allama Iqbal as well, when he said, Ilm ke darya se nikle gota zan gauhar badast. Ilm ke darya se nikle gota zan gauhar badast. वाय नादानी खजफ चीने लबे साहिल हूं मैं. You have to I have translate this. कोई कहता है कि जो divers हैं, the divers jumped into the ocean of truth, and they came out with pearls in their hand, whereas I am just on the seashore. I am just picking at ordinary dross, ordinary material world, ordinary material of this world, which is tantamount to rubbish, whereas the divers have gone into the ocean of truth and picked out these pearls. So in this course, we've just touched the tip of an iceberg, just landed our shuttle on an iceberg. There's a lot to be explored, a lot to be explored. So please remind yourself that grades and exams are not important. You should focus, right? After 5 years, you will not even remember what you scored in E&M, what you scored in mechanics or modern physics. So, enjoy science. Without enjoyment, there can be no brilliance. And without brilliance, there can be no competence. And without competence, we will remain in the poor state of affairs that we currently are. So thank you very much during this semester. Thanks a lot.
जाना पड़ेगा।